Okay, so we are going to talk about the last section in this book, which is acid-base titration. Unfortunately, we aren't together where we could actually do some titrations because it's really kind of fun. Maybe if you take AP chemistry, we can start out with that in the fall. So there are two types of titrations, and actually there's more than two. You can either have a strong acid with a strong base. You can have a weak acid with a strong base, or you could have a weak base with a strong acid. So please add that one to your notes. And one of the things that we want to know about a titration is where the equivalence point is. And what does the equivalence point mean? It means where the moles of acid are equal to the moles of base. It does not, and please write this in your notes, does not mean that the pH is 7. It will not necessarily be neutral. As we talked last time, when you have a weak acid, you create a weak conjugate base, and that will change where that pH, what the pH is at the equivalence point. So please note that the equivalence point is only 7 if you have a strong acid with a strong base. A weak acid would have a pH above 7, and a weak base would have a pH change at below 7. So, going on. Here's an example of a titration with a strong acid with a strong base, hydrochloric acid with sodium hydroxide. And the pH is initially very low, and it would depend on the concentration of the acid where this would start at in terms of pH. And then we would have a gradual rise in pH as we are adding base. The base would be in the burette, and the acid would be in the Erlenmeyer flask below it. We would also have added to that Erlenmeyer flask some kind of an indicator, or we could use a pH probe. In this case, we would be using a pH probe because we have data telling us the pH at each point. And so that equivalence point, like I said, for a strong acid and a strong base would be at 7. It is at the point where we have the greatest or sharpest increase in pH. And we would take the top and the bottom, divide it in half, and we get it 7. And so we would look here is the top of where it's changing. Here is the bottom of where it's changing. And so we would subtract those two and then divide it in half. The amount of base added at the equivalence point is 25 milliliters. If I know the milliliters and the molarity of our NaOH, we can calculate the moles of NaOH. Once we know the moles of NaOH, we would know the volume that we added of HCl, and we could calculate the molarity of the HCl. And typically that's one of the things that I'm going to ask you to do. So eventually, as we're adding base, pH rises. We get to the midpoint of the vertical part of this curve, and that is our equivalence point. And only for strong acids and strong bases is the pH 7 at the equivalence point. You'll notice before 7, when we've only added a few milliliters of sodium hydroxide, the pH is going to be controlled by HCl. After we get to 25 milliliters, now the pH will be controlled by sodium hydroxide. So, what if we take a weak acid with a strong base? Several of the features are similar and some are very different when we have this type of titration curve. And you should be able to identify what kind of acid you have and what kind of base you have just by looking at the titration curve. So here is a acetic acid solution. You'll note first, the first thing that jumps off the page to me is that the starting point is not down at 1 pH, but up closer to 3. Even if they have the same concentration, since acetic acid is a weak acid, it will not completely dissociate, and therefore will not have a pH down at pH 1. We'll notice second, to me, the pH at the equivalence point is not 7. It's out at almost 9. But then if we look at after the equivalence point, the point where sodium hydroxide is now controlling the pH, it looks very similar to the first graph. So there's a gradual rise in pH, and we'll notice what I call this region here, where it's going from about 0 milliliters of sodium hydroxide to about 20 milliliters of sodium hydroxide. This region is called the shoulder region, or this is where buffering is occurring. And what do I mean by buffering? We talked about that in the last unit or last section. We will have it anywhere in this position. We will have acetic acid, but we will also have some of our product, which is the sodium acetate, or the conjugate base of this weak acid. Since we have an acid with its conjugate base as a pair, we have a buffer in this region. Once we use up all of the acetic acid and we get to the equivalence point, now we've converted all of sodium acetate, or our acetic acid has now been all converted to sodium acetate. Now sodium hydroxide will control the pH. There's a couple other interesting features now after the equivalence point. Just like with a strong acid, strong base, this region from about 25 milliliters on is controlled by sodium hydroxide, the pHs. The midpoint in this vertical region is still where our equivalence point is, and the pH at this equivalence point is 8.72. And now sodium hydroxide will control the pH. The other important feature when we're doing a weak acid titration with a strong base is to identify the half equivalence point. And the half equivalence point means pretty much what it says. If this is my equivalence point here at 25 milliliters, then halfway to that point would be 12.5 milliliters, which would be directly in the middle between 10 and 15 here. If we read this graph and go up to our curve, and we can carry this over to our y-axis, this would be the pKa of our acid. And P just means that you take the negative log of whatever comes after it. So pH is the negative log of the hydrogen ion concentration. pKa is the negative log of the Ka for that acid. So if I have an unknown acid and I do this titration, I can identify its Ka by reading the graph and where the half equivalence point is, and identify what that pH is will equal to pKa. Then I can have, and then if I take the inverse of the negative pKa, I will get the Ka for the acid. And so that would be one way of identifying an acid. So 1 or 2 drops of an indicator are added when a sample is being titrated. And we have to select that indicator based on where the pH change should take place. If, as in this graph, it's predicted to be above 7, I would not use the same indicator as if it was in the first titration curve we looked at with hydrochloric acid and sodium hydroxide. So we have to figure out where that equivalence point is expected to select our indicator. And we often call the change, when that indicator changes color, that is the equivalence point, but we also call that the end point when we can indicate or see that color change. So you're going to have to pick an indicator based on what coincides with our expected pH of the equivalence point. So indicators are weak acids. We're only adding a drop or two, so they will not significantly affect our titration, but they give us color, and the human eye is very good at detecting color changes. In fact, we can determine a color change has occurred when it's only about 1% that's changed. of that weak acid. So it doesn't take very much, and we can see that change in color. So here's a list of your indicators. And so if we're expecting, like if we have a weak acid with a strong base, we would select something that would have a pH change, color change somewhere around here. So we would use something like either nitrophenol, or we typically use phenolphthalein because it changes right at that 8.72 for acetic acid, so that would be a really good choice. But you could also use a couple of others. If we have a weak base with a strong acid, we would want to have something that would change somewhere in the 3 to 5 range, and so we might use bromophenol blue is a typical one. You'll notice here it has yellow and then green and then blue. That's because it starts yellow, and as the blue starts appearing, when you mix blue and yellow, you get green. So here's kind of a visual representation of how you would do that. You would want to select or determine where your endpoint's going to be, and then you would pick an indicator that would change in that pH range. Here they're just saying litmus pH range. There are, if we go back up, a number that change right around 7, so you could use phenol red, you could use bromothiamyl blue. Azilarin might be a little difficult because it starts changing so much below pH of 7. So, and then if we're looking at where the equivalence point is expected to be below 7, methyl orange is often what we use. And so, how would you expect a titration curve to look if you started with a base? Would you start with a starting point down here at pH of 1 or 2 or 3? Or would you start with a pH up here about 11, 12, or 13 if you had a weak base in your burette? Or in your reaction flask and you had your acid in the burette? Kind of an interesting question. I would think that through if I were you. So that ends the lecture portion for this chapter. Excuse me. There will probably be more problem videos, especially if you asked for particular ones. So I would be working ahead. And I'm thinking that our test will probably be Thursday or Friday of next week. So thanks for listening and watching, and I will hopefully see you sometime soon.